class this afternoon with Tom Potthink, who will tell us about dynamics near attracting invariant fibers of holomorphic Skew-Products.
Thanks for the introduction, and thanks to the organizers for this opportunity to present some of my research. So today I want to talk about Skew-Products, and everything that I'm going to talk about is based on joint works with Miriam Benini and Jasmine Rithy. So to start off, I want to go over the definition of a Skew-Product. A Skew-Product is a holomorphic map from C2 to C2, where in the first coordinate, we have a function which can depend on both variables, and in the second coordinate, we only depend on the second variable. This is a natural function to look at because it kind of provides a stepping stone between one-dimensional dynamics and two-dimensional dynamics. We'll see more why in a moment. And the goal is to study these kinds of maps to understand at least the dynamics for some class of two-dimensional functions, because an arbitrary two-dimensional function is often too complicated to really study in general, so we want to look at a specific class. One other thing, I'm only looking at holomorphic maps. I'm not restricting myself to polynomial Skew-Products. Usually the Skew-Products I'm interested in are going to be transcendental. Okay, so to study the dynamics, I want to start by looking at the w coordinate. If you iterate this kind of function and then project down to the w coordinate, what you really get is just the function, the w coordinate, so g iterated n times. So this is just one-dimensional dynamics. We understand one-dimensional dynamics to a large degree. And, well, slightly oversimplified, we know that one-dimensional dynamics focuses around periodic points. So it's a natural case to look at to just study specific periodic points. And for this talk, what we're going to focus on is that we have one attracting fixed point. So a point which is mapped to itself as a derivative has modulus less than 1. And we're just going to assume that this is 0, which you can always do up to translation. So if we're in this specific setting where we have g has a fixed point at 0, which is attracting, then when we say that g has an attracting point, so we say that the Skew-Product has an attracting invariant fiber, or we also talk about an attracting Skew-Product. Attracting Skew-Product may not be the perfect terminology because g can have multiple or different periodic points, but this is just to say that we're interested in the dynamics of a Skew-Product near an attracting invariant fiber. So just to start with a few visuals, it will be difficult to visualize anything in 4D, but what you should imagine is that you have a fiber where w is 0, and then this fiber is mapped onto itself by f, because g of 0 is 0, and we want to study the dynamics near this fiber. So that's the w coordinate, and now we want to get to the z coordinate. So once again, we have a Skew-Product, attracting Skew-Product around 0. Now if we introduce a little bit of notation, more specifically if we write fw of z for f of the w, so we write it as a function which is parametrized in w, kind of, then what we get is that if we have a point z0 and we iterate this one n times, and we then project down to the z coordinate, we once again have one-dimensional dynamics, because what we actually have is just f0 iterated n times. So towards our fiber, we have one-dimensional dynamics by g, and on our fiber, we have one-dimensional dynamics described by f0. So what we can then hope, in particular, because 0 is an attracting fixed point, and if we start with a small w, it's going to converge to 0 quite quickly, if you start with a small w, the dynamics in the z coordinate will still behave quite similarly to those of f0. So that's what we hope for, and a slightly different way to look at this is that our f of the w can be written as f0 as our fiber dynamics plus a small perturbation r, which vanishes on the fiber. So then, rephrased again, the question that we try to answer is what is the role of the perturbation for the dynamics of our full Skew-Product? And before I get to the results, I want to specify this connection, because here we just say, okay, it should be approximately the same as f0. What does this approximately actually mean? What's the notion that we want to work with? Well, the notion that we want to work with is the notion of a bulging for two component. And what you have to imagine is that on our fiber, so for w equal to 0, you have a for2 component u. U is a for2 component of f0, and we call it bulging if it extends outwards into a for2 component of the Skew-Product. So if a stable region on the fiber extends outwards into a stable region of the whole Skew-Product. technically, I haven't defined what the Fatou component of a skew product is. You have to be kind of careful to define the Fatou set in higher dimensions, but what you can have in mind is just the usual definition of normality, where either you have locally uniform convergence of iterates or you have uniform divergence to infinity. So this is what we want to study. And the first result is a theorem by Lilov and then later by G, which tells us that if you have an attracting skew product, then the following Fatou components on the fiber always bulge. And those are finite basins of attraction. So a basin of attraction around an attracting fixed point which is not infinity, parabolic basins, and rotation domains. And Lilov was able to show this where 0 is an attracting but not a super attracting fixed point. Or the other way around, Lilov was able to show it for a super attracting fixed point but not for an attracting one. And then later G was able to generalize it to just an attracting fixed point. And what I want to highlight here, what's important, is that these Fatou components are all orbitally bounded Fatou components. So if you start with any point in one of those Fatou components, the orbit stays bounded. These are not all orbitally bounded Fatou components. We can also have orbitally bounded wandering domains, but because we don't know whether they exist, these are essentially, for the moment, all the important ones. This is the first remark. And the second one, the bulging here is completely independent of the perturbation, which is to say, no matter which perturbation we have, as long as we understand the dynamics of F0 and the dynamics of G, we know that the dynamics on the fiber extend outwards. Which is not to say that the perturbation isn't important, because we know that it extends outwards, but we don't know how far it extends outwards. And that's still going to depend on the specific kind of perturbation that we look at. But just the fact that the dynamics extend outwards is independent of the perturbation. So this is what we know for orbitally bounded Fatou components. Then, yes?
So if F0 has, say, an unbounded sequence, that's not real Fatou.
Yes. Or it's not about boundedness of the Fatou components, it's about orbitally boundedness of Fatou components. So if you have a Siegel disk, you always stay orbitally bounded. Yeah. But good question. It's really just about the orbits, not about the Fatou component. The natural question, what happens for orbitally unbounded domains? And, well, the answer, the informal version, we will look at the more formal version in a moment, is if you have an attracting skew product and you have an orbitally bounded Fatou component, then this orbitally unbounded Fatou component, this Fatou component can bulge or not, completely depending on the perturbation. And orbitally unbounded Fatou components, just to recall, are either basins of attraction at infinity, if you have a polynomial function. You can have wandering domains of the escaping or the oscillating variety. So wandering domains either just going to infinity or oscillating between finite limit points and infinity. Or you can have a Baker domain. And a Baker domain is essentially an invariant domain for a transcendental function where orbits escape to infinity. So here, for orbitally unbounded Fatou components, it's always going to depend on our specific perturbation. And I want to talk about the bulging and the non-bulging part separately, and the bulging part is not what I want to focus on. So the easiest example is if you just assume that your perturbation is 0. Then you have a direct product, so the variable doesn't see the W variable and vice versa. So if you have just a direct product, you always have bulging dynamics, which, well, it's a trivial example, but maybe not the most interesting example. And without going into too much detail, in many cases, you can construct classes of perturbations where you still have bulging behavior, but where you have actual skew products and not just direct products. That's the bulging part. And for the rest of this talk, I want to focus on the non-bulging part. So how can we find skew products, and more specifically, how can we find a perturbation where we have non-bulging behavior? So let's look at the actual result. The actual result tells us that if we have an entire function f0, so our fiber dynamics with an orbitally unbounded Fatou component, and if we have our attracting fiber, so we have G with an attracting fixed point at 0, then we can always find a perturbation, so a function, once again, vanishing on the fiber, so that if we combine our different functions into one skew product, we know that U0 does not bulge. So really, given any f0 and given any G, we can construct such a perturbation are. And we were first able to show this for a specific Baker domain. And then later we were able to generalize it for any orbitally unbounded for two component. OK, so I want to give you at least a sketch of the proof. The proof is constructive, so we actually construct such a perturbation. And there are a lot of details which are not very interesting, but I at least try to give you some idea. So just for simplification, we assume that on U0, everything goes uniformly to infinity. We just assumed orbitally unbounded, so we could have oscillating behavior, but the proof is very similar in that case, so we just assume uniform divergence to infinity. And now we want to construct a perturbation to get non-bulging behavior. Well, how do we do this? If we have bulging behavior, then we have normality in the neighborhood. So if everything on the fiber goes uniformly to infinity, then we know that everything in the neighborhood of those for two components on the fiber goes uniformly to infinity. So if it were bulging, everything nearby would also go to infinity. And we want to prevent that. So to get non-bulging behavior, we need to have a perturbation. And we need points arbitrarily close to our two component on the fiber, so that we don't go uniformly to infinity. Well, not going uniformly to infinity just means we go back to some bounded set. And more precisely, what the kind of point that we want is we just want to fix one V0 and U0. So one point on the fiber, and then points arbitrarily close, which get mapped back to a bidisk. So we want to find points Wn, a sequence going to 0, that if we iterate V0, Wn, n+1 times, we get mapped back to the bidisk. So to kind of visualize this, let's look at this image. We have the fiber. For the moment, we have just the fiber. We have our two component U0. By the fiber dynamics F0, this is mapped to a next two component U1, U2, U3, and so on. And we know that this one goes uniformly to infinity. And now we want to find points on top of U0 which get mapped back to the bidisk. So trying to visualize this is kind of difficult, but you have to imagine that the W dimension is towards us. And we then have a point V0, W1, which with the first iteration gets mapped on top of U1, and then it gets mapped back to the bidisk. This is V0, W1. Then we want the next point, V0, W2, which is closer to the fiber, and which gets mapped first to U1, then to U2, and then back to the bidisk. And then we have another point which is even closer to the fiber, which goes to U1, U2, U3, and then back to the bidisk, and so on and so forth. So if U0 were bulging, we would know that all of these points would have to go uniformly to infinity. But if we are able to construct them in such a way, then we know that they can't. I want to mention that technically, for the property that we had on the last slide, we just wanted to get back to the bidisk. And here we are actually doing something more. We construct them in such a way that the points are following the behavior on the fiber. And this is not necessary, but it's just the way that the proof is going to work. OK, so this is the kind of behavior that we want to achieve. What's the main tool that we use? Well, the main tool that we want to use is complex approximation theory. More precisely, we want to use Runge's theorem. And for everyone who doesn't know, Runge's theorem tells that if you have a nice enough set and you have a function on your set, then you can approximate this function by an entire function. So you can go from model functions to entire functions. But it's not too important for the rest of this one. So how do we do the actual construction? We want to use Runge's theorem, which is one-dimensional complex approximation. Our perturbation is two-dimensional, so we make a slight simplification. We write our perturbation as W times H. So we don't have a lot of interaction between W and H. And then we construct H, a one-dimensional function. So what we actually want to do is we want to construct iteratively a sequence of functions, Hn, which do almost what we want our final limit function to do, and then we want to take H as a limit of a sequence. More precisely, if we have an entire function Hn, we want to define the associated skew product, so basically what we want in the end, but instead of H, we use Hn. And we want this one to map the point Z0 WK back to the bidisk, but not all of these points, just the first n many. And if we're able to achieve this, and if we do it carefully enough, we can actually get a limit function, and the limit function not only does it for the first finitely many wk, but does it for all of them at the same time. And to give you an idea of how we construct these functions hk, I want to illustrate how we go from, let's say, h2 to h3. If we have h2 already constructed, then we get a skew product f2 associated to h2. And we have points z0, w1 and z0, w2, which roughly follow the disks and then get mapped back to the bidisk. And now what I want you to notice is that for the behavior, for the orbits of these points, it's only important how our function is defined on u0, u1, and u2. So if we construct our function h3 in such a way that h3 is very, very close to h2 on the sets u0, u1, and u2, then we know that we can basically substitute f2 by f3. So instead of f2, this also holds for f3, which is not 100% true. We have a very small perturbation, but at least the points still land in the bidisk. And once we have done this, we now want to get our w3. And if we choose w3 very, very small, we can, by continuity, we can get it to be mapped along the dynamics of the fiber to u3. And then lastly, we choose h3 on u3 in such a way that we counteract the dynamics on the fiber and get mapped back to the bidisk. And just to iterate how Runge's theorem works here, well, we know how we want h3 to behave on u0, u1, and u2. We know how we want it to behave on u3. We can prescribe this behavior, and then Runge's theorem gives us an entire function which is close enough to still have the same behavior for the orbits. So this completes the proof. So we know that if we can do this, we get non-bulging behavior. This is the main statement, and now I want to talk about a few further questions which are closely related to the main statement. And the first one I would like to talk about is about polynomial skew products. So earlier I talked about the orbitally unbounded for two components, and one of them is a base net infinity. So if f0, if f0 is a polynomial, then we have a base net infinity, and we can use the proof from above. We can use the construction, and we get a perturbation R, so that we have non-bulging behavior. However, this construction, just because we use complex approximation theory, usually leads to a transcendental entire function. So the question that you want to ask ourselves is, well, what happens if R is polynomial? Maybe if R is polynomial, we always have very nice behavior. We cannot have such problems. Well, the answer is unfortunately not. There are examples, quite easy examples actually, where we have non-bulging behavior. One of these is if we have f of zw, which is z squared plus wz cubed, and then, well, 1/2 times w in the w coordinate. And without going into too much detail, the main idea behind this function, why we have kind of non-bulging behavior, is if you imagine that w is very, very small, then compared between z squared and wz cubed, z squared is going to dominate. But if you iterate sufficiently often, then at some point, because in the first coordinate we are squaring, in the second one we are just multiplying by 1/2, suddenly the z term is going to dominate, and then this one is kind of going to explode at one step, which is going to, let's say, introduce a lot of chaotic behavior, which in the end leads to the non-bulging behavior. Because not everything goes to infinity, but there's some dependency. However, even though we have those examples, this one here has a very specific property, which is that the degree of the polynomial degenerates on the invariant fiber. In the first coordinate, we have, well, degree 3 in z. But if w is 0, we just have a quadratic polynomial. And, well, this is important because most people tend to study regular polynomials. And if you have a regular polynomial, you cannot have such a degeneration, because you always have to have extension to projective space. And you can show that for a regular polynomial, you always have a base in at infinity. Once you are outside a large enough disk, you always go very nicely to infinity. And in particular, you always know that the basenet infinity on the fiber always has to bulge. This is the first question. Then the second one I want to talk about is degrees of bulging. And maybe I can use a blackboard for this one. Just to illustrate something. What we, in our construction, we had the two component. Here. With the two component U0 on the fiber, and we selected one point Z0, and then just on top of Z0 we constructed points which do something differently. So just on top we had Z0 WN, and these points we know don't go uniformly to infinity. However, we don't know anything about the areas in between. So you could imagine that you have kind of this behavior, where your F2 component extends at least partially to a larger F2 component, and you just have very selected points where the behavior is breaking. So this is like a pinched, bulging F2 component. And because this could technically be possible, it's useful to introduce a finer gradation. Because for bulging ones, we just said that our F2 component on the fiber has to be in the F2 set. For non-bulging one, it cannot be in the F2 set. It has at least to intersect the Julia set. And then we can introduce two new ones, where we either have partial bulging, where parts of it are on the F2 set of the skew product, and parts on the Julia set, which would correspond to this image here, roughly. And you could also define something like totally non-bulging. The names are still slightly temporary, at least, where every point is a problematic point, and all of them are the Julia set of your skew product. Okay, so we have these different degrees of bulging. And then the last thing I want to talk about.
Sorry, do you, just to go back to the previous slide, so there exists, I called it when I wrote down my question, nowhere bulging, but totally
Nowhere bulging is also a good name, yeah.
There exists totally non-bulging,
Here we have a few examples. Yeah.
but they are presumably transcendental.
Actually, everything seems to suggest that even for this function, it's already totally non-bulging because for the basenet infinity. Basically because of those two growth behaviors, and when one explodes, you really have very chaotic behavior, and this kind of is uniformly enough to get totally non-bulging. And then lastly, I wanted to briefly talk about the global structure of bulge components, which is bulging is a very local property. It's only kind of defined near the fiber. You only know that you extend outwards. You don't know how far you extend outwards or what could potentially happen. So what you can imagine is that, sorry, this is rotated. I needed the space to get everything on one slide. You can imagine that you have different F2 components on your fiber, U0, U1, U2, and U3. And even if you assume that they are bulging, what probably is the most intuitive version is something like this. Every one of those extends into its own F2 component. But what is just as not likely, but also could be possible, is that they all connect into a new F2 component. But even though on the fiber you have different behaviors, they kind of connect outside of the fiber. So we either have them separated or you have them kind of bridging one to the other. And in some cases, for example, if you have a basin of attraction and a pre-image of this basin of attraction, you can quite easily at least construct examples where they connect. Whereas in other cases, in particular if you have like limit behavior going to infinity, if you have a Baker domain and an escaping wandering domain, it's unclear whether maybe they are able to connect or whether that's just a complete impossibility. That's an open question. Okay, that's everything. Thank you.
Any questions?
The construction of the two domains that you are.
So in
So about this, your construction of it's a function R.
Yes.
Can it be arbitrarily close to 0?
The perturbation R.
Yes.
What do you mean by arbitrarily close to 0?
I mean, maybe obtained by arbitrarily small deformation.
I mean, the construction that we have. Hello. So we set R as W times H, and H is the transcendental entire function. So arbitrarily close to 0 is difficult to measure, but you can adjust this construction to have any behavior that you want on a compact set, and then just do the construction outside. So that's maybe one possibility to approach it, but you have to have like growth spikes to a degree to get mapped back to the bidisk, I would say. But it really depends on how you would define arbitrarily close to 0 or arbitrarily small.
Wondering that there is built-in conditions of open condition featured by some perturbation.
So if the conditions stay,
The condition is open condition, meaning that can be triggered by small perturbation.
well, if you use something like compact open topology, then no, because to a certain degree the non-bulging perturbations are very small because they only live near infinity. So it's not an open condition. Bulging is not an open condition if you use compact open topology. Maybe there's a better topology to use, but I haven't thought too much about it.
So those points WN that you struck, right?
Yes.
You send it back. Do they ever do that? Do they live in another particular?
Good question. I mean, it depends on what you do. If you know that your F0 has a basin of attraction at 0 and you go back to the bidisk, then you know that the points get caught in that basin of attraction. But in general, we don't know. We don't know what happens after the k+1's iterate of WK. So it's only important that we don't have this uniform divergence to infinity. Yes.
Can you say something about an example where you have this totally non-movement? Like what's happened to the particular?
For this one here, you mean?
You had the definition about totally non-movement.
Yeah, totally non-bulging, and the example that, well, not the only, but the main example that we have for totally non-bulging is this function, because what you do to show that this one is non-bulging is you have this growth condition, this race almost between these two terms, and this is completely independent of where you start. So you can basically start at any point and you get these, well, chaotic behavior, so you get totally non-bulging.
So can I come again?